So what do you understand by the word transient? So when you connect a DC voltage to a capacitor and resistor connected in series, or an inductor and resistors in series, there is that short time before the current through the circuit and the voltage across the capacitor and resistor, or in case you have an LR circuit, the voltage across the inductor and the resistor stabilizes. So that time before it stabilizes is the transient. So usually it occurs in response to sudden change in the sources that are applied to the circuit. So when there is a sudden change in the source, there is that small time it takes before the voltage across the energy storing elements like the inductor or the capacitor. So in case you have a circuit with an energy storing element like capacitor or inductor, there is that time it takes before the capacitor charges or an EMF is induced in the inductor. So that time is the transient. So we look at how voltage grows in the CR circuit. So when you close the circuit, when you close the switch here, using Kirchhoff's voltage law, V, the DC voltage, will be equals to the voltage across the capacitor plus the voltage drop across the resistor. So that is equation 1. So when you close the circuit here using the Kirchhoff's voltage law, V will be equals to the voltage across the capacitor plus the voltage drop across the resistor. And we know that capacitance equals to charge over C. C, which is capacitance, equals to charge over voltage. So VC will be equals to charge over capacitance, from capacitance equals to charge over C. So we substitute here in the first equation, we substitute for VC, and using Ohm's law, we know that V will be equals to IR. So we substitute here. So after getting this equation, we look at the conditions. What happens when you first close the circuit? So when you first close initially when you first close the circuit, what happens? The capacitor won't charge for some time. So since the capacitor won't charge, charge naught will be equals to 0. So when you substitute this in equation 2, you'll get DC voltage V will be equals to charge, the 0 you've got from substituting for the charge, plus the voltage across the resistor. So initially, DC voltage or will depend on the voltage across the resistor. So the initial current will be I naught will be equals to R. Okay. So the initial current I will be equals to V over R. Can you please mute your audios? So that is the condition, the what? Initially, current will be equals to V over R. So after a certain time, okay. So after some time, e.g. T1, after time T1 seconds, the capacitor will start to charge. So the charge won't be 0, it will be Q1. So the voltage across the capacitor will be equals to Q1 over the capacitance. And the voltage drop across the resistor will be I1 times the resistance. So when you substitute this in equation 1, you'll get the DC voltage will be equals to the to charge 1 over the capacitance plus I1 times the resistance. Then after more time, at time T2 seconds, the capacitor will continue charging. So the charge will increase. The charge will increase and we shall get Q2 over the capacitance. Then the voltage will drop. VR2 will be equals to I2 times R. Then you substitute in equation 1, we get that equation. So then at steady state, when the current has flown for some time, it will stop. At steady state, I will be equals to 0, meaning that the DC voltage will only depend on the capacitor voltage. So when you substitute this into the first equation, since the voltage across the resistor will be 0, we shall only have V equals to VC. So this can be represented in the graph. In the graph here, the graph is the exponential growth curve. When I was starting, I said we are going to look at how the voltage grows in the CR circuit. So now when you look at the curve here, at 0, there is no charge. So VC will be 0. So it's when you see that this curve, VC will be 0. Then after some time, for example, T1, the capacitor will charge. Then VC will also be V1, charge 1 over C. Then it increases at T2, like that, up to when it reaches the steady state. When I equals to 0 and DC voltage will be equals to the voltage across the capacitor. So when you look at this equation here, so you just need to know the equation. You don't need to know how to derive it. So when you look at this exponential growth equation for the capacitor voltage, VC will depend on the steady state, which is V, and also the change in time, the change in voltage over time. So this exponential to power T over CR. CR is capacitance times resistance, which is the same as tau, which is the same as T2 minus T1. So for VC will depend on the capacitor voltage. The capacitor voltage will depend on the DC voltage V at steady state plus the change in voltage over time. That's why we have that tau. So when we look at another graph, the decay curve, the graphs for the decay curves. So we've looked, remember in our circuit, we have the capacitor, we have the resistor, we have the current. So we need to get how the capacitor behaves over time, then the resistor behaves over time, and the current. We've looked at the voltage across the capacitor, how it changes with time. It starts from 0, then it goes on increasing with time up to steady state. But then what about the voltage across the resistor? The voltage across the resistor starts from up. When you look at the curve here, it will start from up, then the voltage will drop, it will drop over time. At steady state, I will be 0, so it will come to 0 also, the voltage. The same applies to this. So when you look at the equation, voltage across the voltage drop across the resistor will only depend on the transient, but it won't have like the steady state like here. V equals to VC, because at steady state we don't have any current, we don't have any IR. So the equation will only depend on the change in time, the voltage, the change in time, voltage change in time over time, voltage change over time. So it will only depend on that. And the current will also depend on that, the change in current over time. The current reduces, it goes on dropping. So we've looked at that. So we look at the time constant for the CR circuit. At steady state, Vc equals to V, and tau, which is T2 minus T1, is the time constant. Time constant is the same as tau, is the same as T2 minus T1, is the same as CR, capacitance times resistance, all in seconds. So we can look at an example. A 20 microfarad capacitor is connected in series with a 50K resistor, and the circuit is connected to a 20V DC supply. The initial value of the current. What is the initial value? Determine the initial value of the current for you. So when we look at our circuit here, you'll see that a 20 microfarad capacitor is connected in series with a 50K ohm resistor, and all connected to a 20V DC voltage. So we say, so they asked us to determine the initial value of the current. And we said, initially, there is no charge. The capacitor doesn't charge. So at initial state, V will depend on the voltage drop across the resistor. So using Ohm's law, I will be V over R. So you substitute for V voltage, 20 V over 50 times 10, which is kilo ohms. Then you get 0.4 milliamps. Then the second question, the time constant of the circuit. We have the capacitance and the resistance. We say the time constant is T2 minus T1 or CR. So we have these two. We don't have T1 and T2, but we have C and R. So we can look for that time constant. We substitute for it, we get 1 second. Then the other question is the value of the current 1 second after connection. So meaning we have T1. We have time. So we need to find current. So we can use one of the decay curves, and one of the decay curves, the equations, I equals to I exponential exponential T over tau. We have tau is 1, T is 1 second. Then we substitute. We have I, we got 0.4 milliamps. So we substitute, we get that. Then the other question is the value of the capacitor voltage 2 seconds after connection. Vc will be equals to V. We use the growth exponential growth curve equation, the equation, Vc equals to V for steady state, then this. So tau, we have tau is 1 second, then we have time 2 seconds. We substitute, we get the answer. The time after connection when the resistor voltage is 15 volts. So from the equation, we looked at just two instances, T1 and T2, but we can look at any other time in between. So the question is, the time after connection when the resistor voltage is 15. So we have the voltage, we need to look for the time. So we use the equation, the resistor voltage equation for that decay curve for the resistor voltage. We have VR 15. We have DC voltage, which is 20. Then we need the time. Then we have tau. We got tau is 1 second. We substitute. Then after we use natural log on both sides, we get the time.